everybody, welcome back. In this video, what I want to do is give you the method for how to do truth trees. Truth trees have the exact same function as truth tables. I find them a little bit more ostensibly intimidating, but in actuality, I think they're easier than truth tables, especially once you get into some longer problems. So here's how you're going to start a truth tree. Just stack the premises of your argument. These are the same ones that I did in the video on the truth tables. This is basically arrow out. We know this is going to work. This is affirming the consequent. We know that this is not going to work. This is going to be invalid, and this is going to be valid. Now, we know that already, but sometimes where doing truth trees or truth tables is helpful is in arguments where you don't know. So, for example, if I'm not going to make you do it, but if we did a truth tree or a truth table for quiz 8's number 9, that is when we're looking at it. Just looking at it, we would have no way of being able to know whether or not this is valid or invalid looking at it. Now, because it's provable and it's on your quiz, it is valid. So you could do a truth tree or a truth table for it that would get you a valid result. But this is basically a check before you get started, like, is this even doable? Okay, before you get into actually doing a proof. That's the purpose of these. So that when we're evaluating arguments and we look at it and go, I don't know, that argument sounds fishy. This is actually a method for, if we transcribe it formally in a correct manner, we can figure out if the argument's valid or not from the get-go. Does this argument actually work? Did someone actually make a valid point? So here's the way that I want you to think about the truth trees. First of all, you've got the list of the tree rules for propositional logic. Those are already there. You'll have these on hand while you're doing quiz 10, which is your final quiz. What I want you to do, though, in terms of method is, first of all, if you can ever, so here's the way this is going to work. If you can ever do any double negation, get that out of the way first. Second, see if you can do any rules that stack. Now, what do I mean by stack? You'll see on the tree rules, basically, there's kinds where it takes a premise, like an arrow, and then it will either split it out or stack it. Every single one of the tree rules is basically De Morgan's law or some kind of conversion like material equivalence. That's really what's going on. Such that, like, what I mean by rules that stack, if you notice the rule like for A and B, if you've got a conjunction, what does it do? It turns into A and B. That stacks. Now, there are other ones that stack as well. Those would include the negated, so a not arrow stacks, conjunction stacks. Then there are others that split and stack. I'll talk about those in a little bit. But basically, if you can do anything that stacks, which would be especially these two, go ahead and get that out of the way. Then see if you can do any rules that split. So if you have anything where it looks like it's doing this, like it splits out. For example, A arrow B, you'll see the tree rule for it. It splits out into not A and B. Basically, what's going on here is you're doing disjunctive implication. You're turning this arrow. Remember, if we go from arrow to inclusive or, what happens is you just change the left negation slot. And you can hear this split as a giant inclusive or symbol that's gotten so heavy that it's flipped over. So yeah, you do that, you're basically turning this into an or. So if you can do any of the split rules, that would include that. Obviously, look at this one. A or B splits into A or B. Nothing magical going on there. And then there are rules that split and stack. And those are ones that have to do with biconditionals or exclusive disjunctions, because as you know through material equivalence, those are actually the same thing. So let's take a look at the method here. So first of all, see if you can do a double negation, get that out of the way. See if you can do rules that stack. See if you can do rules that split. And then finally, see if you can do rules that split and stack. Now, these ones that I have on the board are going to be very, very easy, but they're indicative of the same method that you'll see in the PDF for how to build a truth tree. The method is identical, even though these are simpler. So first of all, when you start a tree, you start by stacking your premises and your conclusion. Just put them into a column. Then the next step is to do this, and this is the part where I've seen many students mess up on this part. A truth tree is kind of like a truth table mixed with an indirect proof. So here's how you start. To start a tree, write your premises, write your conclusion at the bottom. First thing you should do, negate your conclusion. Because what we're trying to do is we're trying to break everything down and see if in our circuits or our tributaries that we're going to make, if everything closes off. So here's what we're going to do. Now we're going to go through this list of things and see if we can break things down anymore. Starting with double negations. Any double knots out here that I need to break down? No. Are there anything that if you look at the tree rules, any things that I can do that break down or into a stack? And the answer is no. I don't have any negated implications or conditionals. I also don't have any conjunctions here. What do I have? So in other words, in short, this can't be broken down anymore. This can't be broken down anymore. This can. What does it do? It's an arrow. If you look at the tree rules for arrows, they split where the left side gets negated. So this breaks down into this. Not A, B. So that's broken down. Now here's what you want to do. Here's how you do a tree, and here's how, using the tree method, you find out if an argument is valid or invalid. Look at each, as things break down, look at each circuit. You can think of these as tributaries like water flowing. What you want in a valid argument is for everything to close off because you want to find a contradiction in the circuit. Okay? So in other words, look here. Are there any opposites in the circuit? Well, yeah. There's A and not A. And what we do is we say, hey, there's a contradiction in the circuit. That breaks down. Are there any opposites in this circuit? Yep. B, not B. Nothing else can be broken down anymore. Everything that we've broken down, we find that there's a contradiction or a set of opposites in the circuit. When that happens, what that means is with a tree is that the argument is valid. Now again, I find this a quicker method than using the truth tables, but some people don't prefer this. What your book has on the issue, it does trees in a little bit of a, I think, a more confusing way. It has what's called one-sided trees, so I don't like to use that. I think this way is actually easier, and so it looks a little bit different than what you might see in the book. This one, let's do the truth tree for this one. Now, we know this argument's valid, and this is what it looks like. With a valid tree, every circuit has a contradiction that closes off the valve. So you can think of this as, is this leaking? Nope. Any place where there would be a valve is tight and good, we're good to go. This one, let's start the tree for this one. Now, we know it's going to be invalid, so it's not going to work. We know that from the tables that we've already done. First step in a tree, negate your conclusion. Then, see if you can break things down anymore using that method. That doesn't break down anymore. That doesn't break down anymore. That does. Look at the tree rule for it, and we use it over here. It's the exact same one. When you got an arrow, you need to split it, negate the left, keep the right. Then what we're going to do is we're going to look up each circuit and see if we have opposites in there. Do we have any opposites in here? Nope. So this is an open branch. I like to think of it as the water. If we're pouring water into this or some kind of liquid, this is leaking. This is a leaking argument. Look over here. Do we have any opposites in this circuit? No. This is leaking too. Now you might be thinking, since we did the table, wait a minute. There were instances when we did the truth table for this where we knew what the counterexample was. We remember when A was false and when B was true. That's how we knew when this argument works. Well, the truth tree also does the same thing. Here it does it in a bit of a redundant manner. Look in this leaking tributary. Every time you see A, what is it? Like anytime you see A by itself, it's always not A. And then B is always B. Look at this one. What is A every time you see it? Not A. What is B every time you see it? Just plain old vanilla B. So this is telling us this argument doesn't work under these conditions. When A is false and when B is true. This confirms it for us. When A is false and B is true, this gives you a leaky argument. That is exactly the same determination that we made with the truth table. That's what truth trees do. They get you the counterexample in this way. You just look at the constituent components, the A's and B's, or whatever your letters are. Once you break them all the way down, what are they in the branch that's open or where it doesn't close off, where it doesn't get a contradiction? Are they themselves in a positive way, or are they negative? Like in this one again. Every time you see A, it has a not in front of it. Okay, every time you see B, it doesn't. So we know that when A is false and when B is true, this argument doesn't work. And thus it's, of course, invalid. And we also know when it's invalid. Here's our counterexample. If the argument is invalid, you always want to state what the counterexample is. And there may be more than one. In this case, it ends up kind of being redundant and telling us in two instances, hey, yeah, this argument's really wrong. Why? Because of this. Also this, which is the same. Just thought you should know, is basically what the tree is telling us here.